Hi guys, today we're going to start with a problem on page 254, number 18. For the problem, we're given this phase diagram. As you can see here, there are multiple pressures and temperatures that are labeled, temperature being on the x-axis and pressure on the y-axis. First, we can start by identifying the three parts of the graph. The darkest part of the graph here is depicting the compound when it's solid. This next part here is when it is liquid, and the lightest part over here is when the chemical compound is a gas. Now, the first question we're asked about the graph is, what is the physical state of the compound at 35 mmHg and at 120 degrees Celsius? So, if we first find the we'll find the point at which 35 intersects with 120 degrees Celsius. So we see here the first pressure we're given is 35 millimeters of mercury. So if we trace that across until we reach 120 degrees Celsius on the opposite axis, we see that that intersection point is in the region of the graph, is in the gaseous region of the graph. So the answer here is gas. Now for the next question, we are asked, what is the normal freezing point of the compound? Now for the freezing point, we just need to find at what temperature normal freezing point is the temperature at which a compound goes from liquid to solid at standard pressure. So standard pressure is either 1 atm or 760 millimeters of mercury. And in this graph, 760 mmHg is depicted here about towards the halfway point. And now we just have to trace it across at the boundary between the solid region and the liquid region. So we see here that temperature where the boundary is at 20 degrees Celsius. Now for the third part of the question, we're asked, what is point A called? So here we have three different points that are labeled on this diagram, point A, B, and C. Now point A here is between the upper region of this diagram between the liquid and the gas areas. So if we see here, now that point A is at the liquid region, so we now see that we can just call point A liquid, as this part of the graph is in the liquid region, so the compound is not a solid, not a gas, but it is liquid. The next part of the question asks what point B is called. Now, point B is a unique point on this diagram because it is not it's not specifically in one part or one region, but rather it touches all three. So this point is known as the triple point. It is a specific part where a specific temperature and specific pressure where the compound is in equilibrium, and it is all three states at once. This is a very rare occurrence. It does not normally happen naturally, but rather it has happened in a lab setting most of the time. So label this the triple point. All right, the next part E, we're asked what point C is called. Now at point C, we see that the temperature is at 120 degrees Celsius and the pressure is 760 millimeters of mercury. So this point is at standard pressure. Now we can also observe that on this diagram at point C lies on the boundary between the liquid and the gas phases. So now that because we know that this is at standard pressure and that this boundary is a phase change, we know that this is called the normal boiling point. So here, write that in, normal boiling point. Okay. So now for the next part, we have to find what change occurs when at a constant pressure of 33 millimeters of mercury and the temperature is decreased from 40 degrees to negative 20 degrees Celsius. So let's find that point on this diagram. We'll start with pressure. So 33 millimeters of mercury is right below 35, so right about here, I would say, on the diagram. And now we know that if we start at 40 degrees, which is probably right after 20 on this diagram, and it decreases all the way to negative 20 degrees. So now we have to try and find what phase change occurs at this point. So if we see that starting at 40 degrees Celsius and 33 millimeters of mercury, the chemical compound is a gas. Now, as the pressure stays constant and as the temperature decreases, we'll see that slowly the compound will start moving towards this phase over here. So it's going to slowly start moving this way. So we see that it goes from a gas over here to a solid. So this tells us that the compound over this change will freeze. So this compound is going to freeze. All right. Now for the second to last problem, we're asked if the solid will float on the liquid. Now, to find this out, we have to look at the slope of the boundary between the solid and liquid phases. So we see here that the slope of this boundary is a positive slope. Now, there could be two different slopes, positive or negative, between these boundaries. And if the slope is positive, that means that the solid phase is less dense than the liquid phase, and vice versa. If the slope of this boundary line is negative, then the solid, if the slope is positive, the solid is more dense. If the slope is negative, the solid will be less dense. So a common example of this is water. Now the phase diagram of water, you'll see this boundary line will actually be negative, so we'll kind of arc up like this. But we don't have, this diagram is not for water, it's for different compounds. So the slope of the line is positive, meaning that the solid will not float as it is more dense. Okay. Now for the last problem, we are asked, can the compound exist as a liquid at 180 degrees Celsius and 2 atm pressure? So let's find this point in the graph first. So 2 atm of pressure here is the highest point on the pressure on the y-axis here. And now we want to find the temperature. So 180 degrees Celsius will be around in between here, in between 120 and 200. So if we find that intersection point, it is going to be right on this. It's going to be right before this boundary here between the liquid and the gas phases. So it should be just about here. So we see that that point is in the liquid region, signifying that the compound can exist as a liquid at this point.